in order to actually drive your motor, you requires a pulse width modulation. Okay, and this is the purpose of the thing. Alright, because actually we can drive our motor, but we cannot vary the power. Alright, it's only full power or no power. We cannot have something in between. Alright, full power or no power. We cannot have something in between them. Alright, or you can say from 0 to your VDD. Okay, I forget already lah, but anyway, some VDD lah. But so in this video, we're gonna use the pulse width to actually help you to vary your power in between, so that you can actually have a better control of your motor speed. Alright, so we'll require a DAC. Alright, just take note, and which is digital to analog converter. Digital will actually control the modulations of your. Later on, you have a graph over here. Alright, so the digital system will actually help you to control this thing, such that the output of the analog will be in correspondence to this particular shape. Later on I will explain, but let's continue first. So the output voltage is equals to your digital input value over your maximum value, alright, divided by your reference voltage. So your voltage reference is times the reference voltage. Your reference voltage is always the voltage coming from your Arduino, I think. Alright, while your digital input value is your value that you want to input, or the speed that you want, alright, divided by the maximum value that the motor can go. So the maximum is the maximum the motor can go, while the digital input is the one that you want to vary it. For example, if it's 0, then 0 divided by maximum value is actually 0, so no power. Alright, if your motor is maximum value is maybe 5, alright, then you set it as 1, then your output will actually be 0.2 of your overall motor speed. Alright, so this is somehow you can actually output your voltage so that your motor can run in a particular voltage. You see? So yeah. But few microcontrollers actually contains DAC, alright, except in some devices intended for particular applications, such as audio. Okay, so therefore in a few microcontrollers, actually they do not have any DAC port. Alright, so be careful of that. Alright, so although you can know how to do DAC, but in fact some microcontrollers do not have DACs. If you really need one, you have to find a separate device and control it from your microcontroller with I2C or a similar interface. So a microcontroller will connect using a I2C bus, alright, and maybe most likely you're talking about another new shield or module to tap on onto your microcontroller. So you require an additional system to tag along with your microcontroller to be better lah. And then the duty cycle of so therefore in order to vary your different speed from no power to full power, you want to vary it in between the no power to the full power. Alright, what we do is actually to vary the duty cycle of a square wave. Okay, and that just take note that your frequency of a square wave must be high enough not to be noticeable. Alright, LED in demonstrations are driven slowly so that PW, the pulse width, is visible. Alright, so if the LED is, for example, it lights up, it waits a while, and then it closes, and suddenly it waits a while, it opens. So we can see it very clearly. Okay, but as for this meaning is that for square wave, your frequency must be high enough such that with your eyes, alright, you have two eyes, your eyes aren't able to see how this pulse width works. Alright, so as you can see, normally at the LED we can see it flashing for one, like bright up and then off and then bright up again, because the frequency is actually quite slow. So we can see the pulse width. You see the pulse width, you on, and then after that over here you close because no light up. After that you on again. So you see this is a pulse width already. Alright, so therefore this is a same thing that is gonna use for your motor. Alright, so let us take a look how this pulse width that we cannot see using a high frequency, such that we cannot see, and also to help you to vary your motor speed. Alright, it's using this thing. Alright, I've been talking about that. So we will vary the length of the pulse. The length of the pulse is this pulse over here. Okay, so if you have a 32 low power, I don't know why is it 32, alright, or I think I know why. It's because you have 256 units. 256 I think is talking about an 8-bit system, alright, which is 255, alright, plus 1 bit, I don't know, but anyway, yeah, at least you get to see a bit stuff, alright. But anyway, if you want a low power, your this thing over here will be very small, right? Because low and keep on all the way is no power. Suddenly you light up again, and then no power, and then light up again, no power, and light up again, no power. Alright, so the no power portion over here, you see, is very big. Alright, so therefore this means that the ones that are high power, alright, are actually very minimum. So we can actually control. So if you want to see super high power, it's always like this, it's always high. Alright, there is no low power at all. Okay, so it's always high. For in this case, as you can see, is some high, and then most of the time is low, then high again, most of the time is low. I think you get what I mean. So for the half power case, is half of the length it's high, half of the length is low. You see? So that's why you have a half power. That's all, 1 to 8. Okay. If you want the average full power, alright, this is full power, but talking about also average power, because it's average of your motor speed lah. Alright, this is written in your catalog. The full average power that your motor can run is about this. So as you can see, most of the time the motor is running, and then the lesser time is actually at rest, and then running again at rest, running again at rest. You see, so most of this time over here is actually at rest, compared to over here, most of the time, compared to here, lesser time is being at high. So over here, lesser time is at low. You see, so this part over here is at low. Alright, for this high power system. At this low power system, most of the high is actually quite short. So we are looking at the length of the pulse. Alright, so this whole thing is 1 pulse. Okay, second pulse, third pulse. So it's trying to talk about pulses. Alright, so I hope that this is pretty good. Alright, we call each of these pulses, we can also call it the duty cycle. Alright, so if it's off, if for example, if this case over here, this is off, then we just call it a off duty cycle. If it's on, then we can just call it a on duty cycle. That's all. Right? It's on or off duty cycle. That's just the meaning. So the pulse width acts, the coding acts like your coding for your LED. If you still remember, so when you turn on an LED, and then you wait a while, and then after you turn off, and then you wait a while, and then you go back to over here, then you flash. It's much like you flash your LED off, and then you on again, and then you on, off. Alright, so it's on, off, like this. So it's the same thing for your pulse width. So now for your Arduino, you also can use this method to actually change your speed. Alright. Arduino of this thing is because you can high and then pause a while, low, pause a while, and then it loops. So this loop actually helps you to save a lot of coding, or instead of going through everything. So by providing a macro in which you can vary the duty cycle easily. So flow code made this easy. Now I think this is the flow of the code lah. So because of the infinite loop, so you loop, and your motor keep running in terms of the pulse width that you want it to be. Alright. So if you want a shorter power, you can have turn on motor. Alright, in this case it's turn on motor. Alright, wait maybe 1 millisecond. Alright, turn off motor. If you want a low power, then wait for maybe 10 millisecond. Alright, so you're like 1 millisecond high, and then 10 millisecond low, and then high again. You see? So this is a low power. So you can vary your waiting time for your high or your low, so that you can create a pulse width. That's just the meaning of that. I think this flow chart is a good testing exam question also. Alright, so I'll just briefly go through is that you set your counter as equals to 0. Alright, and then you turn the load on, and then you have a increment counter, so you plus 1, plus 1. Alright, and then delay for whatever loop that you want. Alright, just as the code that we have written, you delay how many times, you pause how many times. Alright, after that is the counter duty is equals to your counter that you want. If it's yes, then you turn the load off. Okay, so over at this side, it's talking about this side. It's trying to turn this thing on, and at the time when you reach your counter duty, when you count already, you can actually turn it off. Alright, over here this is off. Alright, and the loop goes on. Alright, and this will goes on over here, and the counter period is equals to your period. Alright, so if it reach here, if it's equals to your period, no, then you will loop back up, and yeah, wait alright, so I just repeat again. You turn the load on is over here. You turn it on. Okay, you turn it on. Maybe I should use the red color. You turn it on over here. Okay, and then you increment the counter +1 +++. You delay up to this particular point. Alright, it's your counter duty. So this thing over here is this length over here, this particular length. Alright, or I should zoom in, or I should write it as a yellow color. Alright, this particular length over here is your duty. Alright, is your counter duty. So you count whether is this your length. If it's yes, alright, then you turn the load off. So you turn the load off, which is over here. You turn the load off. Okay, and then after that you go to here. This counter will actually count your period. So there is two type of counter. One counter is to count your duty, one counter is to count your period. Alright, so over here it count your period. Alright, you'll count the full period of this thing. Okay, maybe I should write in the yellow color also. So it counts the full period in yellow color, you see. I think you get what I mean already. So therefore, this counter period keep on, it actually starts from all the way to here already. Alright, so in the end the counter period has its own counter period, which talk about, or which deals with the full period of your cycle. Alright, or the duty cycle talks about only the one that is on high, which is on duty. Which is off duty, then off duty lah. But if it's a duty, just on duty lah. Alright, that's the meaning of that. So counter duty talks about the one when it's high, and then the period counter talks about the full on and off together. Alright, so when you reach your counter period, if it's yes, alright, then you loop back to the reset counter, and then you continue to on again. You turn on the load again, and then you count, you increment your counter, alright, until your counter duty reaches your particular point over here. Alright, so if it's yes, then you turn the load off, and then you go on to your period again, and then you carry on. So it repeats and repeats itself. Okay, so therefore you will need to understand how this thing works. So once you understand this thing works, and I think you can know how to draw this flowchart for yourself already. Okay, so the key thing is that you requires two counter. This is very important. You requires a period counter and a duty counter. Alright, the rest is just to increment the duty cycle over here. Alright, let it be on. How long do you want it to be on? Something like that. If it doesn't reach your duty cycle, then I don't know why, if it never reach my duty counter, alright, if it's no, it actually went to the counter period. Alright, so over here, if it's over here, it actually goes to counting the period, and then it will reset. Okay, so over here it says that if you reach at this point, if you are halfway, alright, for example, if you are halfway, you haven't reached your duty counter yet, and if it's no, because you haven't reached yet so you go to the period. And do you reach your period yet? Because your period over here is this is your period counter. When you reach here, then your counter will say yes, then you restart. So over here it says no, alright, so no, you actually loop back. Alright, so it loops back, and then after that you continue to count and continue to plot until when you reach your counter over here, then everything goes again smoothly, that as and when we say just now. Okay, so I hope this gives you a pretty clear understanding, although it's not very clear, but at least you get a feel of it. And therefore, to actually work the counter, alright, you may require a timer. Alright, you can require one or more timers to actually time the counter. Alright, and therefore you look at the capture compare pulse width module. So you capture the time and then you compare with the time that your motor or whatever that you want. I don't know what the hell, but something like okay. Then it's called the CCP because it's a capture compare pulse width modulation. So it's CCP. Alright. So this is a method to actually help you to generate the waveforms, the waveform over here. Alright, these are the waveforms. So they actually use this timer to actually time at which delay, at which time is this duty on. Why am I having this? Damn it. Wait yeah, okay. So therefore at this time over here, the timer will say that okay, this is maybe 3 seconds. Alright, and then over here this is maybe 2 seconds, things like that. Alright, so on 3 seconds, off 2 seconds. So the timer will actually try to time. So you'll capture, I mean this is the coding. Alright, then you also have another timer to actually capture the real time, whether is it really 3 seconds and 2 seconds, and then you will compare to your code. So you have a code that says that 3 seconds, 2 seconds. However, in real life, for example, if the real life say that okay, maybe not, in realistic case is running 2 seconds, 2 seconds, then you can straight away know the difference that your real life is a bit different from your code. So you need to change your code so that your real life speed will actually go towards the one that you want. Alright, so this is more on the control side of your dynamics and control already lah. So this is something that you're gonna talk about it in something else. So you need to capture and compare your pulse width modulation so that the motor turns to the speed that you want. Alright, so therefore this is called the CCP method. Alright, therefore the timer is like a counter to help you count and compare. That's all it is. Okay, so I think it doesn't. So this page actually explains the previous page flow chart. Alright, in a way that you may want to know. Okay, and so the perils of your, or the disadvantage of your pulse width is actually what? Alright, there's a trade-off between speed and accuracy. So if you want high accuracy, you cannot have a high speed. So if high accuracy, low speed. Why is that so? For example, if you want high accuracy, this means that your duty cycle, the one that is high, alright, will require a larger range, so you can capture it better. So so your counter can capture it better, sharper, so that you know that it is high for how many times. Alright, so maybe if it's, because for example, if you run at a 1 millisecond, or it's way too fast, such that you're unable to actually capture the speed. Alright, but if you were to run at 10 milliseconds or maybe 50 milliseconds, then you can actually capture the speed, stating that okay, the high is actually 50 milliseconds. Alright, but however, because it is running at 50 milliseconds now, which is much higher than 1 millisecond, you see, so the speed actually affected. You see, so the faster speed you cannot capture, the lower speed you can capture, but your speed is being sacrificed to a certain extent. Alright, so if you require a larger duty, or larger, like 50 milliseconds of this length, pulse width length, or you may require a larger period, because if this is considered a small one, then you will require a big one to run this portion over here will be low, right? So if you want a low power, if this is the minimum you can capture, alright, for accuracy, this means you cannot let 50 milliseconds to be the high power thing, right? Because over here, if it's high power, 50 milliseconds, alright, well, maybe this part over here is low, which is 10 milliseconds, then how can you capture this value? Because the most you can capture is 50 milliseconds. Alright, so over here 10 milliseconds you cannot capture anymore. So the system may actually read everything as high. Alright, so you may think, so the system will think that okay, you're running in full power. Alright, but in fact you want to run it in a slower power. So if you want to run it in a slower power, you're gonna minimally set it as 50 millisecond, alright? Or this thing over here, you can actually drag. So this thing over here will be maybe 100 millisecond, which is larger than your minimum one. So therefore you can actually see, or you can capture the time that is being delayed. Alright, so therefore this whole period, alright, is gonna increase. Alright, because in order to capture the full period, you're gonna increase this thing. You see? If happen that you want a low power, alright. So if happen you have one low power, I think you get what I mean already, is it? So for example, minimally I can only capture for 50 millisecond. Alright, I can capture 50 millisecond per frame or something like that. Alright, so over here, maximally over here I can go is only 50 millisecond. So it will be a half power. Okay, if I want a full power, right, over here I need to decrease, correct? Over here I need to decrease. So for full power, this is 10 millisecond, alright, and therefore I cannot capture anymore. So there is a certain constraint that it is. So in order to do that, alright, I gotta increase my 15 millisecond. Maybe it becomes slightly bigger, 100 millisecond. Or at least I can capture already, alright. And over here then I can. Yeah, I don't know how to explain but at least you get. I'm correct okay. So if I want a higher power, I can run it as 100 millisecond. Alright, over here, then I can let it as 50 millisecond. Correct? So as you can see, then over here I can generate a high power system. Okay, but in the slower speed, because this whole overall period is increased. Alright, it becomes 150 millisecond. Alright, comparatively, if you're talking about this thing, 50 millisecond and 10 millisecond, okay, then overall the full period is actually 60 millisecond. So it's more speed, alright, faster. But however, because our system constrained with minimally you can capture only 50 millisecond, so therefore you are unable to actually run in this amount of speed. So you need to increase your this thing in order to reach 100, for example. Then this low will actually is about going by the ratios so at least hopefully you get the meaning of what I'm trying to say. Yeah. Or in other words, the 50 millisecond over here is the restriction. Alright, you cannot have any high or you cannot have any low to be less than 50 millisecond. Alright, if so to speak. Alright, so you minimally you only need them to be 50 millisecond. Alright, if you want in between, either your high to be larger and this one to be 50 millisecond, or this thing over here to be 50 millisecond, while your this thing over here to be larger. Alright, so that you have a low power in this system and you have high power for this system. Because high power, if you take a look, it's like this, right? All the way like that. Alright, for the low power in this case, as you can see, is pretty long. You see? So therefore, this is the key meaning that I just want to convey. So take note that minimally, if you can capture 50 millisecond, then for the high or the low, you can only capture 50 millisecond. Anything lower than that, you cannot do anything. Alright, so you need to increase the period in order to have a variations of your power. Alright, so in this case, if you increase the period, alright, this means your speed is going to be affected. Because if you want to captures means accuracy alright. Because if you want to capture and control your stuff, you need to have a certain accuracy. I mean, in order to be accurate, you need to capture and feedback to your system to tell you whether I use slowing down or what. Alright. So I hope, yeah, a bit shaky but at least you get a feel of it. So whenever you run your pulse width modulation for your motor, you're required to have a CCP module or a CCP library in your Arduino. Alright, so you require a CCP library so that you can actually run a motor. Alright, and the only disadvantage is this particular stuff. Alright, so it's limited by the frequency. Alright, limited by the frequency. Because over here, if you are limited by this over here 50 millisecond, over here this is 50 millisecond, this is actually frequency of 2, right? I don't want I don't want to confuse you lah, but at least you know that the length over here and the length over here, these are all frequencies. The full length over here is considered a period. Alright, so to a certain extent you get to see lah. Alright, I don't know how to explain to you, but at least you get a feel of things. Alright, so therefore the takeaway is that you have limited frequency, and therefore you have limited possibilities. Alright, so therefore this is it for the full understanding of the pulse wave. And next coming up is the remote control servos. So see you there.